Back to ChemCatalyst video. This video is on weak acids. You might have a question. What is a weak acid? Well, folks, a weak acid is an acid that is not strong. And I know that may make a lot of sense, but what does it mean to be strong or weak? Well, if you remember, a strong acid, like gastric juice, which contains primarily hydrochloric acid, which is one of our 7 strong acids, splits up into its H plus and its conjugate base, which is Cl minus, and this conjugate base is incredibly weak, so there's no reverse reaction. It's a one-way street. It's a forward arrow. It's not equilibrium, and this is a strong acid because it completely dissociates. Well, some of the organic acids in lemon juice, like citric acid or cola, which is phosphoric acid, which is not organic, but it's phosphoric acid, and some of the acids in wine and tomatoes and stuff like that, they are what we call weak acids. And they're weak acids because they don't completely dissociate. Well, what does that mean? Well, let's look at, for example, nitric acid, HNO3. Strong acid dissociates completely into H plus and NO3 minus. So it's a strong acid. Strong. All right. However, something like acetic acid, which is the primary component of vinegar, HC2H3O2, is a weak acid, meaning that it is an equilibrium system between this form of the acetic acid and the H plus and the conjugate base of acetate. Okay, now, so what? So what does that mean? What it means, though, is that our pH calculations are going to be a little bit more complex because since the weak acid doesn't fully dissociate, with the nitric acid, if we had 0.1 molar nitric acid, that means we'd have 0.1 molar H plus and 0.1 molar NO3, which we don't care about, but we take the negative log of the H plus, and this would have a pH of 1. Down here, that's not the case, because if we have 0.1 molar acetic acid, not all of it is going to convert to H plus. All right, so some remains undissociated. So that introduces the topic of the Ka. Now, the Ka is just like any other K that we've done. It is the acid dissociation constant, just like Kc was the equilibrium constant. We set it up the same way. So for the reaction in the previous one, HC2H3O2 is in equilibrium with H plus, and the acetate, all of which are aqueous, that's aqueous, and aqueous. Okay, since all of these are aqueous, the K dissociation constant we set up by doing Ka equals concentration of products raised to the power of their coefficient, which is 1, so there's a 1 there, times the acetate, 2 minus, all over the equilibrium concentration of acetic acid. All right. Now, Ka, you can see, is different for different weak acids. So hydrofluoric is a weak acid, and here's its Ka value. And as you go down the table here, these are all weak acids, but they kind of sort of increase in their weakness. That's a weird way to term it. But phenol is a much, much, much weaker acid. I mean, we're talking 6 orders of magnitude weaker than hydrofluoric. And so we can really look at Ka, the extent to which the acid dissociates, and comment on the strength of the weak acid. Strength of the weak acid, that's a weird term, but that's really how we have to think about this. So let's look at a sample problem here. We're going to look at vinegar, okay? Now vinegar happens to have acetic acid. Vinegar is much less concentrated than 2.0 molar acetic acid. But I want to do that one just to start this one off. So we're going to start off with writing the acid dissociation equation. So in this case, we have this vinegar, HC2H3O2. All right, and that is aqueous, and it's going to dissociate into H plus C2H3O2 minus, both of which are aqueous. Now it's time to break out our ice baby chart. ICE. We've got our reaction, and now we're going to have to realize that initially this is 2.0 molar, and this is 0, and this is 0. Now, if you're forgetting ice charts, you got to go back to the equilibrium and learn about what it means to be at chemical equilibrium. But basically, if we're saying we initially have acetic acid, some of it is going to dissociate, meaning that the change would be up by x plus x, because the stoichiometry is 1 to 1. This is going to go down by x, and we end up with 2.0 molar minus x, and then we have x, and then we have x. Well, our Ka expression in this case is, from the previous one, I'm just going to show you so I don't have to rewrite it. This is the Ka expression, H plus times acetate over acetic acid. And the value on the Ka we know, which is actually really helpful, it's 1.8 times 10 to the negative fifth. See, it's right here. So I'm going to write that on the next slide so I don't forget it. Ka equals 1.8 e to the negative fifth, because that's going to help us out. So our K expression would be x times x over 2.0 minus x, so that's x squared over 2.0 minus x. Okay, now I'm just going to do some magic here, and that would be 1.8 e to the negative fifth. All I've done is plug in my Ka value, equals x squared over 2.0 minus x. Now, here's where we have to make an assumption. All right, we're assuming something here, because we could work this out and we could solve for x, and if you like doing that, go for it, but it's going to involve a quadratic. So what I'm going to assume is that x is really small. Okay, I'm going to assume it's what we would say negligible, and if it's negligible, it basically means that, yeah, at equilibrium, this is going to be, still really close to 2. So in regards to significant figures based on the value of Ka, I'm really not removing that much. And that's helpful because that tells us that we don't have to do a quadratic. So really my value for x here is going to be equal to 1.8 e to the negative fifth times 2.0 up to the 1/2. So I'm basically square rooting that to get my x value. And I forgot my calculator. Let me get that. So in order to do that, I do 1.8 e to the negative fifth times 2. And I'm going to square root that. And I made an error. Oops. I get the square root of 3.6. And I get 0.006 as my x value. Now, that's not the pH. I wanted to know the pH, but to get the pH, pH is equal to the negative log, remember that from the last video, of 0.006. Because that's my equilibrium concentration of H plus, my x value, and so my pH in this case is simply the negative log of that, which gives me a pH of 2.22. And we've solved it. All right. Now, I think it's pretty easy to do when you incorporate these. Let's look at one that's a little bit more of a challenge. Let's say we have a particular sample of vinegar that has a pH of 2.90. Now, in this case, if acetic acid is the only acid that the vinegar contains, we want to calculate the concentration of acetic acid in that vinegar. All right, well, in this case, so we're going to be working backwards. So we've got our equation here. All right, this is our same equation here. I'm going to rewrite it here. And it's aqueous again, and it dissociates to H plus and the acetate. Right? And now we know, though, at equilibrium, we want our initial, but we don't know what this is. This is our unknown. We know initially this would have been 0, but the good news is that we do know in this case, that our equilibrium concentration of H plus, we know that the pH is 2.90. So what we can do now is we can take the pH and we can say, okay, I'm going to take 10 to the negative 2.90. It's the antilog of that, which will give me, that's going to give me the concentration of H plus. And in this case, if I do 10 to the negative 2.9, 10 to the negative 2.90, I get an X value equal to 0.0013. So that would give us this concentration 0.0013, and this is 0.0013. This would have been plus X, this would have been plus X, and this would have been minus X. Now, the challenge here is that at equilibrium, I've got some unknown value minus X, but I know what my X value is here. So I probably should have called this Y. It would make it easier, but this value is really going to be our X value that we want to know minus 0.0013. Okay? Now, all of that's going to be equal to the Ka. So the Ka would be equal to 0.0013 times 0.0013. And again, if you're curious where I got this, if I go back to this slide, my Ka is H plus times C2H3O2 minus over the acetic acid. So I put the acetic acid on the bottom, which is X minus 0.0013. Now again, this X is not the same as that X. We've defined this X as being 0.0013 because this went from 0 to 0.0013, it went up. But this is sort of, this X corresponds to the question mark, really, that initial concentration. Now I know in this problem that my Ka doesn't change. It's still 1.8 times 10 to the negative fifth, right? That 1.8 times 10 to the negative fifth. So I can solve for that by just going down here and saying 1.8 e to the negative fifth times X minus 0.0013 equals 0.0013 squared, and the rest is just solving the math on this. So I distribute 1.85, I'm sorry, I distribute that, let's go ahead and clean that up a little bit. I get, that would be 1.8 e to the negative fifth X minus 1.8 e to the negative fifth times 0.0013, which is 2.34 e to the negative 8 equal to 0.0013 squared, which is 1.69 e to the negative 6. Now, this is kind of just a pain in the algebra part, but I can do this. I just need to add to that 2.34 e to the negative 8. And then I get 1.85 I get 1.8, sorry, e to the negative fifth X is equal to 1.71 e to the negative 6, and then I divide to get X, and my X value here is actually my initial concentration. I get 0.095. Now, what does that tell me? Well, that tells me that that is the initial concentration. So I got to put a unit on that. And my molarity of that acetic acid solution is going to be 0.095 molar. So I hope we learned today that strong acids are different from weak acids. Weak acids are acids that do not completely dissociate, and as a result, they are described by Ka. The Ka value gives us some information about the strength of the acid itself, and we set up the Ka just like we do an equilibrium expression where we take the aqueous products and put them over the aqueous reactions. Again, we would not include solids and liquids in this.